Good morning, everyone. There's still people coming into the room. I'm very happy to see Talib and Carrie online. I hope you can see us as well. Yes? You have a good view of who's in the room? Or do you only see me?
We only see you.
That's not good enough. Oh, there you go. Very good. I think we're going to get started, even though some people might still come in. So thank you here for the second part of the workshop on the use of Earth observation for official statistics, mostly on the agricultural side. We have today here with us, and it's remotely with us, but they are with us. We have Talib Kilic from the World Bank and Carrie Mangerson from the Queensland University of Technology in Brisbane. Thank you for being here, and very happy to see you again, Carrie. It's been a while.
It's very good to see you too.
Yeah.
Thank you for the invitation to join this conference. I'm very sorry we're not there in person.
Very happy to have you here remotely. So program of today is we will start off with a presentation discussion with Talib on the 50 by 230 program of the World Bank for the first part, and then after that we'll turn to Carrie Mangerson, where we will start discussing in more detail the training and skills that you would need to be able to do this kind of work with satellite data and data science around that. I'd like to start with Talib. Talib is and let me start with saying that Talib is also one of the co-chairs of the task team on Earth observation for agricultural statistics. But Talib is a senior economist at the World Bank Development Data Group. He's a program manager and a team leader as part of the World Bank Living Standards Measurement Study. And he's also a core team member for the World Development Report 2021, or he was a core team member for the World Development Report 2021 on data for better lives. So his research focuses on poverty, agriculture and gender in low and middle income countries, as well as survey methodology to improve the quality, timeliness and policy relevance of household and farm surveys. In the latter line of work, he focuses on methods for individual level survey data collection, objective measurement, including through sensors, research on policy implications and non-classical measurement errors in survey data, and integration of surveys with geospatial, census, administrative, social media and mobile data are of special interest to Talib. Talib is originally from Turkey, and he has a PhD in economics from the American University in Washington, D.C. Talib, are you ready for your presentation? I will turn over to you. Welcome. It's still evening in Washington, I think, so please go ahead.
Okay. Thank you so much, Ronald. And as Carrie mentioned, we're sorry not to be there in person. In my case, it's health-related issue. I just couldn't travel. Otherwise, I would have been there, and I was otherwise looking forward to meeting you all in person. So thank you again for the opportunity, and thanks for the gracious introduction, Ronald. So I'm going to go ahead and share my screen. So let's see if this will work smoothly. Okay. Can you see it okay?
Yes, yeah, we'll see it.
Okay, excellent. Okay, so thank you all again. So this morning I'm going to speak a bit about the work that we've been doing as part of the, as Ronald mentioned, 50 by 2030 Data Smart Agriculture Initiative. We're going to be talking about the role that surveys can play in calibrating and validating satellite-based methods for high-resolution crop area mapping and crop yield estimation. So for those of you that are not familiar with 2030, 50 by 2030 initiative, it's an initiative that aims to support 50 low and lower middle income countries between now and 2030 to improve availability, quality,
Recording
and
in
use
progress
of agricultural survey data produced by their national statistical systems. And 50 by 30 initiative has three components. It has a data production component, which is basically providing technical assistance to design and implementation of large-scale farm surveys. It has a methods and tools component, which is basically supporting the research that I'm going to be presenting to you this morning, and that particular component is around developing and validating improved methods for increasing the quality, the cost effectiveness, as well as interoperability of survey data, where we have this work program that is around the integration of surveys with satellites for a variety of agricultural monitoring purposes. And then the last component of 50 by 30 is a data use component. So today we're going to be talking about the work that we've been conducting under the methods and tools component, which is implemented by the World Bank. So a bit of background for why we are interested in this topic, and today much of the conversation is going to be about sub-Saharan African contexts, but much of the issues that we're going to be tackling in sub-Saharan Africa pertains to smallholder agriculture, and that continues to be relevant in much of the developing world. Needless to say, agriculture is key to rural livelihoods. In the case of sub-Saharan Africa, it can contribute up to 85% of the rural household income. So, to monitor progress towards national and international goals in agriculture, we need accurate measures of crop areas, production, as well as crop yields. Not only at the national level, but with sufficient within-country disaggregation. So these data can guide targeting as well as evaluations of policies and interventions, not only in agriculture, but also in social protection, as well as disaster risk management. However, in many lower-income countries that rely on smallholder farming, that also need the agricultural productivity improvements the most, the required data are either not available or considered unreliable. So what has been a game changer over the last few years that can help fill data gaps is the dramatic increase in the high resolution satellite imagery, both free imagery that is provided by governments, as well as gated imagery that is acquired by the private sector. A good example is a European Space Agency Sentinel-2 twin satellites, which you see on the right side, and these twin satellites are providing 10-meter resolution imagery for the entire Earth every 5 days, and they are doing that for free. So as a result, we started observing agricultural plots in smallholder farming systems with clarity that we could not have fathomed just a few years ago. But still, we need data to be able to train and validate satellite-based models that are applied to these high-resolution satellite imagery to obtain agricultural data and statistics with improved spatial and temporal resolution. Now, recent research on satellite-based monitoring of agricultural outcomes in smallholder farming systems can be grouped into two camps based on the source of their training data, right? So the first strand of research is largely a collection of studies that have used manually labeled satellite imagery. And these manual labels largely pertain to land cover types, while the second strand, a growing set of studies, used georeferenced ground data, mostly from existing surveys or new surveys that were commissioned in the context of these studies to train and validate remote sensing models, right? So today's talk is related to this second strand of Earth observation applications that rely on surveys to meet training data needs. Now, there are a few takeaways from the literature, particularly in this literature that is central to the work that I'm going to be presenting today. First, training data actually do affect the quality and the spatial resolution of satellite-based estimates, right? So we've done this work in Uganda and separately replicated the similar research design in Mali, and that particular result was fairly cross-country consistent. Here's one of the key findings I'd like to share from one of our papers in Uganda that was published a couple of years ago now in American Journal of Agricultural Economics. It's also open access. So here we're looking at two different plots. On the one side, I am plotting full plot objective crop cut based yields that are obtained on the ground against a calibrated satellite yield measure that is using these full plot crop cuts for calibration purposes, right? On the right-hand side, I'm plotting again for these same plot locations, the full plot crop cut yield obtained from the ground, this time with uncalibrated satellite yield estimates that are purely based on satellite imagery as well as crop models without using any training data. So what you can see is that in both cases, right, both the calibrated as well as the uncalibrated satellite yields do actually a comparable job and also a fair job in explaining plot level variability in crop cut yields, right? So roughly around 54-55% R-squared we're seeing here. And these are estimates based on Sentinel-2 imagery. And the plots that we're talking about here, on average, about 1/5 of an hectare. So tiny plots that are very characteristic of the smallholder agriculture in Uganda. But the big difference between the two graphs is that these uncalibrated estimates are systematically shifted to the right, and they're systematically overestimating the true yield on the ground. So you can see here that while the yield variability is captured well by the uncalibrated estimates, the fact that we are calibrating them basically avoids this overestimation issue that would otherwise be there when we're using uncalibrated estimates that do not rely on survey data. Now, second, we've seen also from the literature that much of the research has actually been conducted at subnational levels, right? And it has exhibited quite a bit of heterogeneity in terms of the type of training data that they were using, as well as the approach that they followed in collecting these training data in the context of the surveys. And third, we know that recurrent large-scale surveys could provide opportunities, right, to address shortcomings in training data for Earth observation applications, but there are currently no clear recommendations on survey methods, fieldwork protocols that can generate the right training data, right, from these recurrent large-scale agricultural surveys that are conducted by countries, particularly, for instance, in the context of the surveys that would be supported by the 50 by 30 initiative. So These requirements we expect to vary, right, based on the outcome that we're trying to monitor. Say crop area mapping versus crop yield estimation, which also, in a sense, indicates the difficulty, but also the necessity of coming up with these guidelines such that we can position recurrent survey data collection in such a way that it can actually provide data that is also useful for these downstream Earth observation applications. So with that background in mind, as I mentioned, we have this work program that's ongoing under the 50 by 30 initiative on integration of surveys and satellites. We're seeking various objectives and working on a number of deliverables, but essentially we are supporting rigorous research activities to answer some high priority questions in how microdata should be collected, analyzed, and disseminated in a way that these surveys can then help scale up some of these integrated satellite survey applications for Earth observation. So as part of this research, we are focusing on an attainable set of agricultural outcomes in terms of mapping. So we're interested in looking at cultivated areas as well as yields, and for a minimum of 4 cereal crops. But in essence, as I will showcase, we also expanded the focus to some additional cereal crops in some select countries that the research has been conducted in. And the main output, basically, with all of this research, we would like to put out as these guidelines for the georeferenced microdata collection and processing for calibrating and validating these remote sensing models for high resolution crop type mapping and crop yield estimation purposes. And obviously, there's going to be additional outputs in the form of other working papers and peer-reviewed journal articles that inform these guidelines. We're going to be producing, and we have already produced for some countries, high resolution seasonal crop area and crop yield maps for the countries and the crops that are covered by our research. And we make these maps available, publicly available, not gated, so open access at 10-meter resolution. And then lastly, but not least, we're going to be making available these georeference training data sets that we use for our research for downstream use in other Earth observation applications. And these data are going to be confidential, but we're going to be making them available through non-disclosure agreements and through the World Bank Development Data Hub, in collaboration with the national statistical offices that have provided the survey data that inform our research. One final note. So in all of this, we do have a technical partner on this work program that is working alongside us, which is a firm based in the United States called Atlas AI. Now, just a few high-level notes in terms of our achievements to date. So I included here the link to the open access kind of research article that was published in Remote Sensing now a bit more than a year ago. And today we're going to be recapping the main findings that are stemming from this paper. But basically in this first phase and also the ongoing period, we've undertaken research to answer several operational and interrelated research questions in the context of satellite-based maize area mapping in Malawi and in Ethiopia, right? So the first question we were interested in answering is how much training data we need to reach an acceptable level of accuracy of a crop classification algorithm. Second, we were wanting to know how the approach to georeferencing plot locations on the ground impact algorithmic accuracy. And lastly, we were also curious about whether and how the type of satellite data and exclusion of plots under specific area thresholds actually would affect our algorithmic accuracy. This area threshold question always comes up, particularly in smallholder settings, because of the concern regarding small plots and this mismatch between the scale of the plot vis-a-vis the resolution of the high resolution satellite that we're using. In this case, it's Sentinel-2 imagery. So we wanted to see if the predictive accuracy would be different, right, in different types of training data sets that we could create that would exclude, say, small plots from a training data set, and then would allow us to look at that resulting predictive accuracy in a comparative fashion vis-a-vis a setting where we exclude no plots on the basis of area. So answering these questions obviously is important, not only for assessing the utility of existing georeference household survey data, which we sometimes hear there's data sources that are actually currently available that could be considered for use, but we don't know how fit for purpose they are, right? And until we have some of the answers to these questions, we can't really assess whether the existing data are fit for purpose. But most importantly, answering these questions would allow us to inform the design of future large-scale surveys that could provide the required training and validation data for downstream Earth observation applications. So, as I mentioned, some of the outputs of this work will be in the form of these crop area and crop yield maps, which will be forthcoming. But in the case of crop area, tied to this particular paper, we've already made available 10-meter resolution for several seasons, maize and crop area maps for Malawi and Ethiopia through World Bank Development Data Hub. Currently, currently we're carrying out this work, but for a while we've been working on this extension of the research to crop area mapping for alternative crops and in alternative countries, as well as to crop yield estimation, so that we can, start compiling these recommendations across a number of different crops beyond maize, and for not only for crop area mapping, but for a crop yield estimation as well. And finally, a number of these research activities also directly inform the activities and work planning of the Joint Task Team on Earth observation that Ronald mentioned at the beginning of the call. So I have a number of slides that will be recapping basically what we have done in this particular paper, and then I'll end with what we're going to be doing looking forward. So as I said, our interest was on the marriage of survey data with satellite imagery. So to start answering these operational questions, we rely on a range of survey as well as geospatial data and a unique machine learning framework that we set up for this purpose. So let's start with survey data. So the georeferenced plot level survey data that we use for our research stem from nationally representative multi-topic surveys that were implemented by the Malawi National Statistical Office and the Central Statistical Agency of Ethiopia, whose new name actually is the Ethiopian Statistical Service, under the World Bank LSMS-ISA initiative, basically an initiative that we've been implementing, we've implemented prior to the 50 by 2030 initiative over the last 10 years that have supported NSOs in Sub-Saharan Africa in designing and implementing longitudinal household surveys with a focus on agriculture. So in the case of Malawi, we are using two different surveys. So the first survey is the Integrated Household Panel Survey, which was implemented in 2019. So this is a longitudinal sample that dates back to 2010. The previous waves were implemented in 2013, 2010, 2013, and 2016. We're not using the data from those earlier waves to match the availability of Sentinel-2 imagery. IHPS covered about 3,000 households and attempted to collect GPS-based boundaries of plots that are basically cultivated by households that are engaged in agriculture during the 2018-19 reference season. And in addition to full plot boundary location, the survey also, as has been the tradition in the context of LSMS-ISA surveys, also captured the plot corner point at which the GPS-based area measurement actually commenced on the ground. So the second survey from Malawi is the fifth integrated household survey, which is implemented in parallel with the IHPS, slightly on a longer fieldwork duration, 12 months. In 2019-20. The big difference is that this is a cross-sectional sample. It's a single visit survey that covered about 11,000 households, collected information either on the 2017-18 or 18-19 season, depending on when the households were visited. And that also attempted to collect these GPS-based plot boundaries for cultivated plots, as well as the plot corner point, right? And then finally, in Ethiopia, we relied on the Ethiopia Socioeconomic Survey, which was implemented in 2018-19. So this is also a longitudinal survey, but in 18-19, it was the baseline for a new longitudinal sample. The season that they reported on was the 2018 Meher season, which is the main agricultural season in Ethiopia. And in Ethiopia, we don't have plot boundaries, but we just have a single plot corner point at which they commence the GPS-based plot area measurement. Now, having said all of this, I think it's important to note that these are existing data that we assess to be fit for purpose. So these are not surveys that we designed and implemented to support Earth observation applications, but clearly, especially in the case of Malawi, where actually I was personally overseeing the work program, we had this interest in intensifying georeference data collection to support these kinds of applications. So it was an opportune time for us to look back and look at some of the more recent existing survey data sets that were basically assessed to be fit for purpose that later we were able to use for our research purposes. And a second point to keep in mind is that these are surveys with sampling designs that are driven by representation at the national and the regional level in terms of household consumption, expenditures, and poverty, right? So these are large sample surveys, and because of the percentage of rural population that are in these countries and the incidence of participation in agriculture being near universal, these surveys do actually yield large samples of agricultural households and extensive data on their agricultural activities. Okay, so with this work, obviously we start out with isolating the best quality data that is available for analysis. So here we start with Malawi. First of all, we retain plot records only if they possess a corner point as well as a full plot boundary, and had a crop type record for the reference agricultural season. Crop type record meaning we know which crops were cultivated on each plot, right? So if the location information, either the corner point or the plot boundary or both, was duplicated, right, across 2 or more plots in each household, we dropped all duplicated records, except in cases where one and only one of the duplicate records had a high degree of confidence. assigned to their location data quality. And in these cases, the record with the high degree of confidence was kept. And lastly, only records with a high degree of confidence in the location data quality, both for the corner point as well as the plot boundary, as indicated by a metric that is provided by these handheld GPS units, were retained. So in table 1 and 2, we see the IHPS and separately the IHS5 rainy season plot observations, broken down by georeferenced information availability and by maize cultivation status. So we end up retaining just over 50% of the plot sample in both surveys. The excluded observations are more mainly due to absence of plot boundaries, right, followed by a georeferenced data quality issue. So this indicates a need to strengthen the training and supervision of enumerators that are tasked with collection of georeferenced plot boundaries when they visit the plot locations. In the retained analysis sample, approximately 72% of these plots were cultivated with maize in each agricultural season across the 2 surveys. In the case of Ethiopia, we retain plot records only if they possess the corner point information. As I indicated, we don't have plot boundaries in Ethiopia. So the research is more limited in the case of Ethiopia. And in Ethiopia, we follow the same steps in terms of assessing the quality of the georeferenced information. In tables 3 and 4, again, we look at the breakdown in terms of georeferenced information availability and the maize cultivation status. In Ethiopia, we retain close to 90% of the plot sample for analysis, since we have a lower threshold for, in terms of meeting the information requirements, because we don't have the boundaries to begin with. And the plot level incidence of maize is actually much lower in Ethiopia. It's estimated at 16%, but due to the large sample, we still have close to 2,000 plots that are cultivated with maize. Okay, so based on the survey data, we can simulate actually different data collection scenarios that vary the approach to georeferencing plot locations on the ground, which is basically summarized on the left side, or we can create different scenarios that exclude small plots under specific area thresholds, and also different scenarios that could vary, the amount of training data that we are using for our models. So on geolocation specifically, on the left side of this slide, we work with plot boundaries, right, that are available to us in the case of Malawi, and we derive 6 simulated alternatives, right, plus the single corner point that is already captured by the enumerator. So based on the plot boundary specifically, we derive the centroid of that plot, again exposed, and then compute the value of each geospatial predictor for the pixel with that centroid. Another variant, which is denoted as the plot mean, it basically computes the mean value of each geospatial predictor across all of the pixels within that boundary. Okay. Plot points is randomly sampling 20% of the pixels within that particular plot boundary, and then uses each pixel as a separate data point in the training data set. Boundary points uses each pixel associated with each corner point that is derived from the plot boundary, okay? As if we went around the boundary of the plot and only georeferenced the corner points. And finally, the Hall mean computes the mean value. The Hall mean computes the mean value of each geospatial predictor across the pixels within the boundary that is constructed out of these deduced corner points. So not the exact plot boundary, but an approximation of it. And the convex hull basically, again, samples 20% of the pixels within this approximated field boundary. Now, few notes about our input imagery and the geospatial predictors that we're using. On satellite data, we are relying on Sentinel-2 optical features, as well as Sentinel-1 radar features at 10-meter resolution. We used harmonic regressions to process a time series of these satellite features. Obviously, for every plot location, we have these measures for specific geospatial indicators of interest captured across the agricultural season. So we can actually use harmonic regressions to come up with fitted distributions of each indicator of interest. So in this particular case, we're looking at maize, groundnut, and soybean plots, and the GCVI, which is one of the vegetation indices, and the approximated, fitted distributions as a result of these harmonic regressions. These harmonic regressions allow us to capture phenological metrics by fitting a harmonic curve, like to these observations throughout the agricultural season. And we're looking at a range of satellite-based indices. So on the left-hand side, you'll see them in terms of the indices that we're looking at: the GCVI, the MBR1, NDTI, and NDVI. So we're looking at a range of satellite-based indices as well as other metrics. But we're also bringing in other ancillary geospatial data, right, that are matched with our plot locations that are also otherwise available across space, right? So we have information on elevation, the slope, the aspect, the temperature, and most notably the precipitation. So this information again is matched, these are available time series, right? So these are matched to plot locations, and in the case of the vegetation indices, these are products that are derived from the satellite imagery, where we are overlaying plot boundaries on the imagery, and then we are basically extracting the derived features in accordance with the location of the plot boundary, and basically definitions of these simulated scenarios that I shared with you. Okay, now a bit about the modeling that we used for this first paper on crop area mapping. Now in Malawi, basically across all of the different dimensions of experimentation that we created exposed, we ended up with over 26,000 scenarios, right? So you can basically see that, okay, we have 7 geolocation methods, as I have very quickly explained. We have 50 data subsets, right? From 2% to 100% subsets of the training data. We increase that at 2 percentage points. In effect, you have these 50 data sets that you're working with. We have 5 different area thresholds. So basically, for each of these data sets that we have created, we also have different versions that exclude certain plots as a function of their area. We have this feature type dimension where we are looking at optical only, radar only, and both optical and radar information that we're using in our modeling. And then for every combination across these 4 dimensions, the geolocation methods, the training data set size, the area thresholds, and 3 feature types, we're running 5 replications, right? So across all of that, we have this 26,000 scenarios that we have to make sense of. In Ethiopia, it's more limited because we don't have the plot boundaries, so we only work with one geolocation method, and based actually on the results that we've gotten from Malawi, there are certain decisions that we've took in terms of eliminating the area threshold exercise and only working with optical data. And again, we're doing the same exercise in terms of the training data subset sample that we're varying, and we're doing everything 5 times to capture variability, to minimize variability due to random sampling. So in each country, what we do is we separate 70% of the survey data for training the model, another 15% for model tuning, called the validation sample, and the remaining 15% is for comparing the observed crop cultivation pattern to the one that is predicted by the model. So that 15% is the test sample, right? So the plots are randomly segmented into these 3 bins: the training data, the validation data, and the test sample in each district, right? So that the spatial distribution of plots in training, validation, and test samples are comparable, like across space, which is basically what we are showing here. A being the number of plots across districts that are in the training sample. B is for the validation sample, and C is for the test sample. And this is the very summary overview of the machine learning pipeline that we apply to each of these data scenarios to identify the areas on the ground that are cultivated with maize, right? So we're combining training data from surveys with a series of vegetation indices that are computed from Sentinel-2 imagery for the reference season of interest in each survey. And along with a range of other geospatial variables that are computed for these plot locations, including weather metrics, elevation and slope, and the model performance is then evaluated by comparing observed and predicted outcomes for the 15% survey sample that is used for testing purposes, and our machine learning model is a random forest, model. So we can talk more about that if there are any questions. But I wanted to get to some of the main findings. So I'm gonna try and wrap it up in the next 7-8 minutes or so. So here are some headline findings, and I'm not sure if this is adequately visible, but with less than 1,000 plots, which is basically around 15% of the training data, these multi-point approaches actually perform better. And those are the ones that I highlighted here in red, the boundary points and the plot points. Around 2,000 plots, which is about 30% of the training data, the aggregation approaches, which is the plot mean, and that's on the plot based on the plot boundary, or the hull mean based on all corner points. They outperform all available approaches. Remember, the plot mean is basically the actual boundary that is captured by the enumerator, and basically summary of all of the pixels that is within that boundary for a given geospatial predictor of interest. And the hull mean is basically that deduced plot boundary on the basis of the plot corner points that we detect from the actual plot boundaries. And again, doing the same kind of aggregation exercise within that kind of approximated boundary. Now, another interesting, I think, result from this data, from this analysis is that we need roughly 7,000 plots with a single corner point to reach the same level of accuracy with 3,000 plots under these aggregation approaches, right? Plot mean and hull mean. And here are actually accuracy metric is the Matthews correlation coefficient, the MCC, which is basically what you see plotted in this graph. And another aspect of this analysis is that you can kind of see the extent to which the model learns as you infuse more training data, right? That the model could be trained with. So something that you can also appreciate with these georeferencing methods that are kind of outperforming other alternatives is that they tend to also have the fastest learning, right? As you infuse more data, so you can kind of appreciate that declining percentage change in the Matthews correlation coefficient as we add more plots into the mix. One other key finding that we were able to showcase is that the peak performance, which is basically what we define to be reaching at least 90% of the best MCC estimate that we can achieve for a given model. So that peak performance actually could be achieved with only 60% of the training data, right? So we also don't need all of the training data at our disposal, and obviously that is welcome news from a cost effectiveness standpoint, because these information that we're asking the enumerators to collect, obviously requires visits to plot locations to capture those plot boundaries, right? So under the preferred basically approach, as well as the Hall mean, which is the second best, we just need about 60% of the training data. But both of those preferred approaches, they require the plot boundary. Okay. Now the centroid method, which is basically the single point method, right? We see that it outperforms the single corner point method. So basically what that means is that if only a single georeference point can be collected, it should be near the center of the plot as deduced by the enumerator. And that's, we label that to be the third best option. So there's some additional findings we have regarding the plot size, which I emphasized at the beginning because of this concern around the mismatch between the scale of the plot and the resolution of the imagery. Now, kind of interestingly, what we find, and actually this is relatively cross-country consistent and also consistent for other crops as well, which I'm not going to be showing today, but we see that excluding actual plots that is based on any sort of artificial area threshold, and remember we experimented with 5 different area thresholds, it actually reduces algorithmic accuracy across the board, and this is fairly consistent across all geolocation methods except for the convex hull. And that's likely because of the geometrical approximation of the plot boundaries based on these plot corner points, right? But for the most part, we don't recommend to exclude any plot from measurement based on size, right? Even in these contexts where the average plot sizes do tend to be on the smaller side. And on satellite type, we document that the model performance tends to be highest actually when we're using optical data alone, as opposed to using radar data or using radar data combined with optical data. So these findings do not necessarily justify the additional investment in processing the radar data, which is normally appealing, right? In contexts where we have persisting cloud cover and the radar can penetrate that cloud cover, but we don't actually see a very distinct benefit in this research of bringing in the additional radar information. So the optical imagery itself seems to be sufficient. Now, what we see here is that actually in these slides, what we try to make sense of in comparing different geolocation methods and their interactions with the different constraints that we've imposed, the estimated accuracy statistics were seemingly small, right? So Now, what you can see here is that, again, I listed here all of the geolocation methods and the best performing model for each geolocation method. And what you can see is that, the out of sample accuracy measure we have in this case, which is the Matrix correlation coefficient, it's not so different, right? So at the extreme, there's like 5% difference, right, in the middle column of this table. But even that seemingly kind of small, insignificant difference can actually lead to large differences in total maze area estimate in Malawi. And obviously that has significant downstream implications for policy making. So we see that the model performance is highest while using survey data with full plot boundaries, right? All corner points. And those resulting estimates are the most conservative, actually, in terms of the total area that is cultivated with maize, right? And next, the multi-point methods overclassify the most, okay? And looking at measures of total area with disagreement vis-a-vis the best performing model, we see again the value of achieving small performance gains with better training data. So here we're doing a pixel by pixel comparison at 10-meter resolution, right, for the entire country, tallying up the pixels, right, with discordant values for the presence of maize cultivation vis-a-vis the map that is generated with the best performing model, right? So the extent of total disagreement can actually range from 500,000 hectares to about 1 million hectare, right, under less preferred approaches to georeferencing on the ground. So just a quick recap of what we've seen today. So we showcased based on this existing survey data and through integration with satellite imagery, collecting a complete plot boundary is preferable, right, in terms of georeferencing of plot locations in large-scale surveys. And this is particularly true if the collection capacity is limited to fewer locations. Remember that, the same performance that we can achieve with 3,000 full plot boundaries can only be achieved with 7,000 corner points. So if you're collecting less, do it well. So seemingly small erosion in classification accuracy under less preferable approaches, right, to georeferencing locations consistently results in total area under maize cultivation to be overestimated, and that ranges from anywhere from close to 0.2 to 0.5 million hectares. So that's about 8 to 24% overestimation. So small performance gains are worth the investment. If you cannot collect the complete plot boundary, a second best strategy is georeferencing the complete set of plot corners, which can then be used in approximating the full plot boundary. The classification performance peaked with about 60% of the training data under the preferable as well as the second best options. And if a single point can be collected, that should be near the plot centroid rather than the plot corner. And with large data sets, actually, the performance should be comparable to that of complete plot boundaries. And lastly, as we've seen, we don't recommend excluding any plot observations on the basis of area thresholds, and we seem to be doing fine enough with just optical information alone. So as I mentioned, there's some data assets that we made available tied to this work. They're accessible on the Development Data Hub, so feel free to check it out. So we have several seasonal maps for crop areas and maize areas for Ethiopia and Malawi. This is just a very quick overview of what that looks like. So just a quick notes about what we're doing right now. So we're scaling, we're scaling this up to an additional country, but also additional crops to identify training data requirements for crops that are beyond maize. we're replicating a similar research design for understanding basically training data requirements for high resolution yield estimation. And there we're working with data sets from Mali and Malawi with a focus on maize and millet. As part of this research, we are gauging the sensitivity of our recommendations to the choice of the model. What I presented is purely based on a random forest approach, but in this ongoing work for both crop area mapping as well as the crop yield estimation, we're also trying a convolutional neural network, and we're also trying to see whether the scope of the geospatial covariates that we're using has a bearing on our predictive accuracy. In the case of yield prediction, we will also do a systematic comparison of, as I showcased at the very beginning, uncalibrated versus calibrated crop yield estimates, right? To, again, provide some additional information about the value of calibration. And then we've conducted this follow-up activity, which is still ongoing in Uganda. And this was basically a large-scale georeference plot outline data collection, as well as crop cutting activity that was piggybacked onto the ongoing Uganda household integrated survey. So there are a number of outputs and activities that will be upcoming, which we will be highlighting for you all, hopefully in the very near future. So I mentioned we'll be putting out these guidelines for basically targeting mainly NSOs and survey practitioners on how microdata, primarily these plot-specific information, should be georeferenced on the ground to feed into downstream Earth observation applications. We'll generate additional crop area and crop yield maps for different crops and different seasons for Ethiopia, Malawi, and Mali. I mentioned these georeference training data sets that we are basically using for our research that will also be made available alongside the crop area and the crop yield maps, but these will be gated products, so you will need to request for access and then go through the process of signing a data access and a non-disclosure agreement to be able to use the data for downstream research purposes. And then there will be several working papers and peer-reviewed articles. And obviously, we'll keep looking at the new data from Uganda and also incorporate that into the eventually updating of the guidelines. And we'd like to do more work, basically in support of these research questions in a setting, at least in one setting outside of Africa. So, and again, with a focus on smallholder agriculture. So if there's any interested colleagues in this space, particularly in the Asian context, that would like to talk more, please let me know. So with that, back to you, Roland, and you.
First of all, thank you for the presentation. Yes, what I would like to do is have a round of questions here. Let me start off myself just to see if I well understand what you have presented. And I think you went into very much detail. I also want to say, Talib, that it fits well with what Lorenzo was saying yesterday. I think the two presentations fit from one to the other. So one question I have while looking at it is also, so if you would have a dedicated agricultural survey on the plots, right, how much better would this get than taking it from the household surveys that you have done? So, and did you maybe compare some notes with FAO on this, who'd done some work in Senegal and Uganda? Yeah, so one general observation, I think, on a logical point is that if you have less accurate training information, as you showed, the estimations of yield are larger, or production, and I guess the idea is that this is all based on probability and machine learning, and if you have less accurate input information, there could still be a bigger plot out there, whereas if you have clear boundaries, then your model will reduce the size of the plot. So I just, if you had some reflections on that, on why there is a systematic conservative estimate, as you said, for if you have clear boundaries of the plots. And then finally, you mentioned earlier on that the resolution of the satellite imagery that you would have might have an influence. I mean, you've worked with Sentinel-2 data. How much better would results be if you would have at least some part of more higher resolution data? So I also don't know if there had been internal discussions on that topic as well. So that's for the start of. Please go ahead, Talib.
Okay, Ronald, thanks. Yeah, thanks so much for the questions. Okay, I'll start with the last question. I'll work backwards. So on this idea of actually looking at the sensitivity of our findings in accordance with the resolution of the satellite imagery, it's a very good point. We unfortunately can't do that in the context of this research because we're using well. We might be able to. We just haven't really looked at it. The reason why I'm saying that is because obviously with high resolution satellite imagery, they're typically commissioned, and if they're not commissioned, we have to look into their archival data. That's not going to be free, so it's going to be available for purchase. And even if you're working with the archival data, you know, you may have gaps in terms of cloud cover, right? Availability of the imagery. There might be mismatch in terms of the timing of the image that you need, right? And the timing of the image that they have in their archive. So it's very difficult to execute that research design retrospectively. But in one context, at least in the case of Mali, we did actually look at it. Now, Mali is not a typical smallholder context in the case of Africa because plot sizes are on average much bigger and they tend to also more monocrop. So in the case of Mali, right, so the average plot size there is like 1.5 hectare, like compared to Uganda, which is 0.2 hectare. So with that resolution, and this is also documented in one of our papers, with that scale of agriculture, we have looked at basically sub-meter resolution digital globe imagery that we've commissioned for our plot locations. And we basically did the yield prediction with digital globe imagery. And actually at that time, we had some kind of more coarse resolution imagery from Planet, but still higher resolution than Sentinel. And then we also had the Sentinel imagery for the same locations. And for that scale of agriculture, we were not seeing the benefit of using higher resolution stuff, right? So I can't tell you how that would look in Malawi and Uganda, and obviously that's an open question, right? Now, in terms of this, the comparative assessment that I've shared, right? So one of the things that I should have clarified is that there we're taking the estimates that tend to be most conservative, which basically are generated with the best performing models of the bunch to be the benchmark. So because I don't have this like benchmark that sits outside of the system that tells me exactly what the truth is. So I'm doing that comparative assessment only in the context of the models that I'm evaluating. And in that one, I'm just taking the model that has the best MCC score, and and that just happens to give me the and along with other like full plot boundary based alternatives, it just gives me the more conservative estimate. And everything else that has lower predictive accuracy vis-a-vis that model tends to overestimate maize areas under cultivation. Okay. Now, on your first question, like on ag surveys. Like the utility of ag surveys versus household surveys, right? So clearly, household surveys, right, they're not necessarily the first source of information that you would go right, to elicit this kind of data. We're using household surveys in this case because data exists, they're fit for purpose. You know, this was done in the middle of COVID, so we couldn't actually go to the field to do our own data collection. So we were working with a number of like unique constraints at that time, but in the case of these household surveys, because of where they're conducted and because of the incidence of participation in agriculture in the rural space, and because of these surveys being large samples, you actually end up having very decent sized agricultural household right samples that you can actually work with. Now, clearly, what we showcase here in terms of the requirements of data collection, they just have to be picked up first and foremost by the agricultural survey. So this is why in the context of the 50 by 30 initiative, whatever that we push right to be the best practice, we want that to be shared with the NSO partners and basically familiarize with the NSO partners for them to adopt it in the context of their operations, right? So one last thing I will say on this point, which is the fact that even for the agricultural surveys, right, these are often list frame based samples, right? So they're cases in which agricultural surveys are based on area samples, but by and large, in low-income country context, they're still list frame samples. So, which means that, right, in addition to that, they are basically, we're thinking about different types of variables that typically inform the sampling design for a large-scale farm survey. And they tend to be generally around the population of agricultural households. Now, you can think that if you designed a survey, if you designed a data collection effort in isolation from everything else, right, purely for the purpose of meeting ground data needs to training the best, like to training a model in the best way possible, your approach to sampling design would be different, right? And it will depend heavily on the application. So the spatial sampling approach, right, for something that would be designed in isolation would also be different than an agricultural survey. Now, with the recurrent surveys, I think it's not very realistic to think that they can shoulder a lot more burden than they already are. So that's why what I'm saying is that, of course, we can always come up with even a better sampling scheme that meets better the requirements of the Earth observation applications, but in reality, that may not be within the reach, right? Because of the availability of resources and the recurrent survey activities. So still, these ACT surveys that are recurrently implemented, I think they are a potential source of training data. And in this particular case, you know, in an environment where we have such drastic constraints on the availability of training data, they are sort of a valuable resource, right? So anyway, okay, back to you.
Thank you. Questions from the room? Yes. Our colleague from Morocco.
Hello, thank you very much. It was an interesting presentation. I have two small questions. We know that before each census, each country do a cartography work in which they go through all the buildings, etc. In your opinion, is there a way to combine these efforts with means to create a training data for satellites or Earth observation imagery? This is the first question. And also regarding the indicators you showed, do they apply only to country level, or do they apply also in a large scale level? Thank you very much.
Okay, Ronald, should I answer? Should I pick
please
that
go
up?
ahead. Yeah.
Okay, great. Thank you so much for the excellent question. First of all, on the question regarding the cartography, obviously, you know, that work is central, like in general, is central to the successful implementation of the census, but the geospatial information that is actually generated in the process could be of downstream use, right? So I like that idea a lot, and clearly the one thing that I will emphasize is that cartography work, I guess, gets done every 10 years, right? Around the census preparation time. So the kind of information that you would need, I guess, for the types of applications that we're talking about, they tend to be season specific, and in a way, one thing that we have not actually discussed today is how much information you can use from a prior season to predict into the subsequent one, right? Or like how much information do you have to accumulate over time to be able to say, okay, this is a season I can miss for some reason. Say you didn't collect the data on georeference plot boundaries, but you have sufficient data that you've accumulated right prior that you can actually use to still train the model and be able to come up with reliable estimates. So with something like cartography work, right, it happens at a given point in time. So probably some limited mapping could be done, but the way that the cartography operations are organized, right? So these are not meant to be surveys, like data collection exercises, like in the case of a census. They're generally undertaken with a different objective and with different skill sets, right, in terms of the people that are on the ground. So if you want to use a cartography operation to collect this kind of data, probably it wouldn't be my first pick, but if you need to do it, you do need to train the people, right? And you may need to think about the team composition that you're sending, because it may not be the right people, right, to collect the data that you need, or to interview the households. But clearly, at the moment in which you have boots on the ground, if you wanna take advantage of that opportunity, right, to collect some data, it could be done, but it has to be with the right, I guess, human resource requirements. So yes, but with some qualifiers. One of the things actually I will say with the cartography work is that it's not so essentially related to agriculture, but this availability of shape files for enumeration areas, like digitized shape files for the enumeration areas, is actually a point of it's all. I mean, I find in low-income countries in particular, these files are not very accessible. So if you ask me like what should be done as part of the cartography work and as an extension of it, probably the first thing that I will say is that let's get those digitized enumeration area shapefiles, and let's make sure that they're accessible. So that would be my first pick, right? And then I can probably think about agriculture, but that's first and foremost on my mind. So on the indicators themselves, like the final kind of resulting products of all this work are kind of gridded products, right? So I mentioned like 10-meter resolution. So they have entire country coverage. So they're not like a single statistic. You can create a single statistic for an entire country or maybe regions of that country, but the resulting data is actually much richer than that, right? And because they're going to be gridded products, and you can have for very specific locations in the country, and you can also disaggregate. Basically, you can achieve certain level of disaggregation of statistics, which you cannot otherwise achieve with the survey data.
Thank you.
Yeah.
Thank you for the clear answer. I have two more questions, and there we go. So we got Elio and we got our colleague from Mauritius. But first, Elio, over here from INEGI Mexico.
Thank you for your presentation, and I would like to ask a few questions. First of all, if you consider that these guidelines depends on the machine learning algorithm, I see that you in your conclusions mentioned that neural networks may not the same behavior that random forest, and maybe these guidelines depends on that the choice of the algorithm. The other question is if you have tried to use unsupervised machine learning methods to identify the parcels as a pre-processing stage of the analysis. And the last one is I see I couldn't see the values in your plots, and I didn't see how was the best performance you get for the best combination, and if you think that this level of performance is adequate to generate official statistics in agriculture. Thank you.
I will ask the colleague from Mauritius also to pose the question. Can somebody give a microphone? It's over there. Yeah.
Good morning, everybody. Talis, thank you very much for this very good presentation, very rich in information. I am from Mauritius. It's a small island. I have a couple of questions. You know, in Mauritius, the NSO, Statistic Mauritius, there's a census agriculture and some agricultural survey. Say we do the cost of production survey. But as regards to yield estimate, production for crops in general, it is a land ministry, it is a Ministry of Agriculture. So my question is whether NSO can do their own independent yield estimate and also for area estimate, and would that be conflicting with land ministry? My second question is when you say about yield estimate, which crops are relevant, I mean, to do, what are appropriate to do yield estimate? I say in the case of I say maize and sorghum, so it looks like they are typical crops that we can use this technology. And third question is about, is a request, where can we have the guideline on the methodological approach? Because you have been talking about household survey, and then we have the farm survey. You know, household survey is normally for agriculture it's about establishment survey. So agricultural farm survey, so it's agricultural establishment survey. So I'm a bit confused by using the household survey approach in the case of using the training data. Thank you very much.
Thank you. Talib, back to you.
Okay, excellent. Thank you. Yeah, thanks so much for all the thoughtful questions. So I'll start with Elio's questions. So yeah, clearly, in terms of the guidelines that we want to put out, we do want to assess the sensitivity of our findings to the modeling approach. So what I presented today didn't look at that, but in the context of a wider range of crops and for both crop area mapping and crop yield estimation, we do want to compare whether our recommendations would be different, right, for ground data collection purposes if the modeling approach is a random forest or more of a black box type in the case of the CNN, right? So that work is ongoing. But I have to say that maybe I can, obviously I can share the findings with you today. You'll just have to take my word for it, but then we'll publish the results anyway in a few months. It's actually not so clear what the benefit is. I mean, as far as the emerging results are concerned, what the benefit is for a CNN. So something that is computationally less complex, like in the context of the random forest, appears to be doing just as well. So at least that's some of maybe the preliminary insights that are coming up from our work. So at some point, on your second question, at some point we did have these aspirations around also kind of seeing whether we can validate some approaches to automatically deduce plot boundaries from satellite imagery, because we have the actual plot boundaries, right? And we can apply an algorithm to, you know, create deduced plot boundaries, and then we can match the actual against the predicted. We unfortunately abandoned that. I think it's an interesting idea, but it's very tough. It's a very tough one. And I'm happy to exchange more thoughts about this, you know, if you're interested. And on the, like, on your last question, which is a loaded one, you know, this idea of like how much predictive accuracy is, you know, what should be the level of predictive accuracy for us to be using these estimates as official statistics. I feel like I don't really have a good answer for you. So I don't have a good answer for you partly because I feel that we do need a body of work kind of coming together, and we do need to, I think, have that discussion as a community. So I can give you some very speculative personal opinions, but they would be speculative, and I would be sort of uncomfortable doing that in a way. But it would be great if we can actually talk more systematically about this across several applications and the accuracy levels that they're reaching to come up with some recommendations around minimum levels of accuracy that we would expect from models. But it's a very important point that's also very operationally relevant. We need to discuss as a community. Okay, colleague from Mauritius, I'm sorry I missed your name, but yeah, thank you. Yeah, thank you for your question. So now, you know, in these countries, I think, well, in the case of the in the case of Malawi, Uganda, Ethiopia. Now, in these cases, the NSO is reporting agricultural production statistics, right? So, but in the case of Mali, for instance, it's not. It's the ministry. So, in every country, and I see the responsibility for doing work on agricultural statistics is not always. It doesn't always lie with the NSO. So I just wanted to note that. I think it's an important point, because to the extent that the data production responsibility lies with the ministry, then the guidelines that we're producing, right? They also have we also need to be reaching out to I guess additional stakeholders, like to socialize them with what we're saying. So I think that's an important point. Now, these guidelines that I mentioned, obviously, you know, we're using household surveys to carry out certain types of analyses, right, in the interim. But I expect these guidelines to be relevant for adoption in the context of agricultural surveys first and foremost, right? So I wanted to clarify that in terms of the target, the ultimate target of the guidelines, and the surveys that we're trying to first and foremost impact. And lastly, on which crops are relevant, it's an interesting question. I think, you know, probably, yeah, depending on the, so first of all, depending on the context, but also depending on a specific sets of interests, presumably multiple crops may be relevant, right, in a given country setting. So here we're opportunistic, because we're saying we're only looking at cereal crops, and there's a reason for that, because doing this work for tree crops, permanent crops, it's a lot more difficult. So in a way, we're working on cereal crops, and in the case of these cereal crops, right, in these like African countries, none of them are, for instance, rice, like heavy rice producing regions, right? But when you come over to Asian contexts, East Asia, South Asia, the Pacific, some other crops rise in prominence. And for some of them, right, we're looking at here staple crops that are cereal, but there are other crops that probably this kind of work should be done for, and presumably it could be more difficult to do. A good example would be cassava, right? So think about, like, it's already nightmarish to measure agricultural production and productivity for cassava on the ground, and we're trying to do that with satellites, and I think it would be difficult. But I think that's it's another question. I feel like it's a key question in terms of which crops should we be targeting, and a part of that question is like, well, we also need to be thinking about crops where we need to intensify the research to exactly figure out how we should go about doing this kind of work. Okay.
Very much. Yes, thank you very much, Talib, for those answers. Regarding the program, we're a little bit over time, so we will stop it here. I would like to ask everyone to give a round of applause for Talib. I think it was excellent. Thank you, Talib. I know you can't stay with us for more time, but thank you very much for being here, and we'll pick up all of these the topics again with the task team on Earth observation over the coming time. Thank you.
Yeah, that sounds good, and thank you again for the excellent questions. And if any of you all have follow-up questions or comments, please feel free to email me. And otherwise, have a good rest of the day, and speak to you soon.
Thank you very much.
Thanks.
We're going to turn to Carrie. Carrie, you're still with us?
I am. Hello, can you hear me?
Yes. Thank you for being with us and for being patient here. One thing I wanted to check first with you, Carrie, is how much time you have. Just to be sure, it's like I think it's around lunchtime where you are. Is that correct?
That's right. Yes.
Yeah. So are you restricted in time? Just to know.
Yes, so I can talk for however long is useful. Ronald, if you prefer that we stick to schedule, then I can speak for about half an hour, and that will get you back on schedule. It's up to you.
No. I was more concerned about that. Maybe you had some obligations as of 2 o'clock your time. But no, okay, no, that's good. Because I'm also conscious of the fact that I will not allow any coffee break right now. I think we're going to go right in here, and we'll do the coffee break after we'll have the discussion with Carrie. So Professor Carrie Mangerson has been working with our committee of experts for quite some time, specifically on two task teams, the task teams on Earth observation for official statistics, but also the task team on capacity development, competencies and skills. And that's also what we will be talking about now. So this is about building, so that's the title of this segment, is Building Geospatial Data Science Training Courses Based on User Profiles. So Carrie has done some very interesting work on that in Australia, and has also shared that with the task team on capacity development. So, Carrie, if you can lead us through that, please. And maybe you can give a little bit more background. So you're in Queensland University of Technology, and you're a professor of mathematics, but maybe you can give a few more details of your work as well in Australia. Thank you.
Okay, thank you. So I'm a professor, distinguished professor of statistics here at the Queensland University of Technology. I'm also the director of the Centre for Data Science here at the university. I've been involved with the UN Global Working Group for probably about 10 years now, or maybe slightly less, but and also then part of the task team on the use of satellite data for agricultural purposes. So in particular on crop identification and prediction of crop yield. The particular work is both in the methodology, but I won't talk about that today, but also in the training area. And so trying to understand how we might develop a training program, given that there are many people that are interested in using these kinds of data, both the technical aspects of it and also then the communication and implementation of the outputs for official statistics purposes. And so as part of the task team then, we've been looking at ways that we can utilise mostly online information so that then it becomes freely available for everybody across the world. So I'd like to talk a little bit about that work, and I'll first share my screen and we can start. And I'm presuming you can see my screen.
Yes, yes, we see, not in presentation mode yet, but we see your presentation.
Okay, okay.
And now it's presentation
So now,
mode. It's good.
perfect, thank you, good. And so this is this work is in collaboration with a colleague of mine here at QUT, Amy Stringer, and also Lorenzo De Simone, which you heard yesterday, or who you heard yesterday from FAO. So what I'd like to talk about in this is to showcase an introductory video that was created through the UN and also UNITAR, showcasing the role of Earth observation data in producing agricultural statistics. I'll follow that up then with an overview of the development of the task team personalised training program that we have developed. And if we have time, show a tutorial on the use of that personalised training program, but we can come back to that. And then finally, some conclusions and acknowledgements. So for this video, I'm going to see if this works and tell me if we can actually, if you can hear the sound of this, please. Can you hear the sound?
It's not coming up. Maybe we have the technical team. Can you help on this, or it might be difficult? Can you put the? I don't know, Carrie, if it would help if you put the link in the chat, and then it will be run from this side.
Oh, sure, that's fine. Oh, hang on. Okay, let me try putting that in the chat then.
Okay, now, okay, well, okay, it came up, the video, but anyway, so, all right.
Oh, did it?
It did. It maybe just takes a long time.
Okay, perhaps I can put it in the chat anyway.
Yes.
Would that be okay?
Yes, please, go ahead.
All right. You just bring this up then. I'm sorry about this, Ronald.
No problem, yeah.
Okay, I've just put it in the chat there, as you will see. And I'll stop sharing. And hopefully you can play it from there. But otherwise it's in the chat, Ronald, and so people may be able to access it themselves.
Yeah, it's hybrid mode here, so we actually don't have access to the Zoom, but our technical colleagues have, so they will play it from there. They will let me know. Otherwise, I think we were just not patient enough when you clicked on it. I think it was coming up, but it just took a while.
Oh, I see. Okay, sure. If it takes too long, I can keep talking and then.
Yeah, maybe continue, and then we'll come back to that. Yeah.
Okay, we can show it at the end, perhaps, if that's reasonable.
Okay.
Okay. All right. So let me get back to this then. Okay. So what I'd like to do then is to show an overview of the task team training program. And the terms of reference for this were to support member countries by helping to develop new methods for the collection, analysis and use of new data sources such as Earth observation data for evidence-based decision-making in support of national policies and international agreements. And the focus for the task team was on the SDG goal target 2.4, which was by 2030 to ensure sustainable food production systems and implement resilient agricultural practices that increase productivity and production, that help maintain ecosystems, that strengthen capacity for adaptation to climate change, extreme weather, drought, flooding, and other disasters, and that progressively improve land and soil quality. And the indicator 2.4.1 is the proportion of agricultural area under productive and sustainable agriculture. So this was the motivation then for the task team and the use then of Earth observation data. So the trusted methods here were around the analysis of analysis-ready data and production-ready data for satellite-based Earth observation data for estimation of crop types, areas and yields, and land use management and land use change. And the training here was to look at developing training material on the use of methods and algorithms to estimate crop types and crop yields. So the training approach that we used here was to utilize the global expertise of trusted online publicly available courses. We can create new courses through the Global Working Group, but what we wanted to do was to say there is actually quite a lot of courses that are available online now. And how can we take advantage of those courses to provide training, in particular for different sectors that wish to upskill in this area, but who come from different bases. Perhaps it's managers, perhaps it's more technical people, perhaps it's the practitioners and so on. Knowing that there is a lot of material online is one thing, but to understand what material is actually useful for a particular person is another thing. And so this training approach was to be able to identify what courses would be most useful for what sectors, and to be able to then to develop a training program, a personalised training program based on these publicly available courses. So phase one is then to define user profiles and knowledge areas and to collate the existing online training programs from trusted sources, and then to create this personalised training program based on these existing courses. Phase two then is to add United Nations overview courses to introduce these training modules, and then phase three is to embed the training program in the United Nations global platform. Where we're up to at the moment is we've undertaken phase one and actually embedded phase one outputs into the United Nations global platform under phase three. And we're now in discussions and planning about phase two. That's in line with the United Nations Global Working Group around creating a body of training modules across the different task teams. So the user profiles then that we were considered were three. So a data analyst, management, and a GIS expert. So for each of these user profiles then, we developed different knowledge areas. And so for Earth observation for agriculture, the main knowledge areas that we identified were in the use of software, visualization, remote sensing, GIS, data management, and data analysis. So the idea is then to find courses relating to each of those. So we searched the available online courses and identified them for each of those roles, as for example, a manager or for GIS, what the professional background for the course is, what is the use case in those courses, what software was used for those courses, and what the programming language was. So you can see here, for example, the role of a manager for one particular course. It was more targeted at a manager. It was all professional backgrounds. The use case was for Earth observation and GIS, a high-level introduction. It included no software and no programming language. So that particular course then was classified with these sorts of tags. For another course then, the GIS role it was more suited for, it was for all professional backgrounds under GIS and looked at land cover mapping using supervised methods for desktop users. It used particular software and then referred to Python as a programming language, but not very deep in programming in Python. So each of the courses then were tagged or described like this. So this is an example then of more courses, and you can just see here the type of things that, the type of courses and the type of tags that were attached to them. So, so for example, you can see for GIS or for a manager, what kind of courses, what kind of background, what kind of use cases, what kind of software, what kind of programming language. So if we take this then, we can fit this now into those knowledge areas. And so understanding for each of the, like for remote sensing, software, visualization, GIS, data management or data analysis, whether this course was an introductory course, an intermediate course or an advanced course, and how those courses fitted together under those headings. And then grouping those courses under a topic, for example, remote sensing for agriculture. If we go deep dive into those modules, then, for example, you see, because this picture here is quite small, of course, so we just zoom in on the remote sensing part of this, and you can see that under fundamental then are the fundamentals of remote sensing. So these are the courses that are going to be involved just in the fundamentals. Then other courses will be more introductory, so satellites and sensors, precipitation and soil moisture, data and data products and indices, and other courses will be more intermediate. So under precipitation, for example, it will be about, the courses are about evapotranspiration and vegetation, and under data products and indices, courses to do with field sampling and examples. And then there's the advanced stream. So courses, for example, under the precipitation and evapotranspiration, advanced courses may be use cases for data products and integration with software like R and computing indices. So courses that really become more technical or more advanced. Similarly, under the data products and indices, field sampling and examples for intermediate level, but then more detailed examples at the advanced level. So you can see that by tagging the courses and by grouping them in this way, we start to develop a program of learning that can cater to the more fundamental, the more introductory, the more intermediate, and the more advanced learners. So under each of those then, we can look at what are the courses actually containing, what's the content of the courses, and starting to then understand how we could put these together. For example, the overall goal in the remote sensing module is to teach people how to handle satellite imagery. The fundamental courses then talk about what is remote sensing, what are some of the agricultural applications, what data do we have access to. Moving to the introductory courses will be questions like, what is this data product and why do we measure it? Where can I find this data? How might I use this data? And how do I calculate indices? The intermediate course then will talk about what are some examples of remote sensing in agriculture, for example, water resources management, and how to do field sampling. And finally, the advanced courses focus more on more detailed examples, bringing the knowledge gained so far together, and the software that can be used to handle this kind of data. So we then look at, for each of the courses, agricultural courses, spatial statistics courses, and so on, the key, so this is whether we've investigated them or not, who provided that course. So for example, there are many courses by NASA or the EU, what the course name is, what the level is it entry level, intermediate, and so on. Who is this course targeted towards, according to our managers or the GIS experts and so on? Whether what the mode is this free and online, and that's what we focused on. What kind of software was used and what prerequisites there were. So each of the courses then were tagged like this. So you can see that there's a sort of a large database sitting now tagging these courses that are available online. An example of this is through Lorenzo's work, where looking at crop mapping using the Centu Agri toolbox. And so we looked at here the learning goals, what would be in the fundamentals, what would be in the introductory, what would be in the intermediate and the advanced cases or levels for this particular goal. And you can see here on this slide the different topics that would be covered under each of those kinds of levels. So this is an example of if you were to be thinking about using a particular tool like crop mapping using the Centu Agri toolbox and trying to understand how do I learn the techniques and the background in order to be able to use this toolbox, then you can access this, this learning module and say, at what level am I at here? And what courses then, what topics do I need to cover? And then being able to search for the courses that cover those topics, the online publicly available courses. So what we have then is this personalized self-learning system. We have a user profile and we have these knowledge areas. And the personalized self-learning system says, what is your profile? What level are you now on a scale from 1 to 5 in terms of your basic knowledge, computing, data acquisition, data processing, data analysis, and GIS? So, and what level do you want to be? Where do you want to upskill? So some people may this person wants to upskill in basic knowledge. They're quite comfortable with their level of computing and data acquisition. They're quite good at collecting data. They'd like to learn a little bit more about data processing and some more about data analysis and also some more about GIS. And so this is asking each individual sort of say which type of information or upskilling would they like to take to acquire. And from that then comes a set of recommended courses. So for this particular person, the recommended courses would be a University of Helsinki Auto GIS courses in computing and GIS skills, and an Esri course, a MOOC, a massive online course on spatial data science that would provide the data processing and data analysis skills. And that would then bring them from the level that they are now to the level that they want to be using these online courses. So the next step then in this is to extend this audit of trusted online training courses and integrate in particular to look at the work that is being done by the regions. So there's a lot of courses that are being offered in regions in the UN, and we want to take advantage of those courses because often those courses are more specific to the types of conditions and the types of training that's required in those particular regions. So integrating those courses into the database and then refining this prototype personalised self-learning system with sharing more ideas with the UN for further development of this learning system, and then to design some certification around this in collaboration with the United Nations to acknowledge the work and the upskilling and the learning of people who've been taking these training courses online. So that's work to come yet. So there is a tutorial video on this that I'd be happy to share. I just note that the sound isn't travelling through. We can try this in a minute, but I'm wondering, Ronald, if the video might be ready now if I stop sharing.
Thank you. Yeah, can you try to click from your side? I think it was just loading up. Might be still in your system somewhere. Let's see if it works.
On my side? Sure.
Yeah, can you try?
Let me see. I might see if I can do it from Zoom, actually.
Yeah.
Oh, sorry, from my side here. Tell me if you can hear this, please.
We see it. We don't have sound at the moment. No, the sound is not coming through. Do we? I'm looking here at the technical people here. Do you think you can run it from this side?
We can show it here.
Yes, you can show it.
Yeah.
Please go ahead. You can grab the screen and then run it from this side. Yep, we're starting.
Agriculture is key to the world's.
Do you have sound?
Agriculture, or farming, includes cultivating plants and crops and rearing animals to provide food, wool and other products. Agriculture plays an integral role in social systems and culture, business and industry, economics and politics, and local and international food security. The global importance of agriculture is highlighted in many international documents, such as the Annual Statistical Yearbook and the Report on the State of Food and Agriculture, both presented by the Food and Agriculture Organization, or FAO, of the United Nations. Accurate estimates and forecasts of agricultural activity are a vital component of every country's official statistics. However, it can often be difficult to obtain these estimates using traditional ground-based methods. This may be due to the complexity or geographic dispersion of the statistical units to be surveyed, as well as limitations in road connectivity, technology, or budget. Ground-based data collection can also be affected by broader adverse climate or political events. In these cases, Earth observation, or remote sensing, can be used to improve the spatial estimation and prediction of agricultural activity. Indeed, even if ground observations are available, Earth observation data can improve official estimates. The last decade has seen improved satellite technology, increased access to freely available Earth observation data, and better analytic tools. It's now possible for all national statistics offices to use Earth observation data to develop cost-effective estimation, monitoring and forecasting programs that can complement their official agricultural statistics and report on a wide range of SDGs. For statistical officers with an institutional mission to characterise statistical phenomena, Earth observation data can be used to improve national statistical estimates and compare with international estimates. They can also be used to contrast the information collected in the field, which can lead to improvements in the supervision of the data collection or adjustments to non-sampling errors, for example. For statistical officers with a broader mission, Earth observation data can be used to produce forecasts or obtain risk estimates, such as the geographic approximation of areas at risk of disasters. A major use of Earth observation in agriculture is for mapping and monitoring crops. This includes remote identification of the type of crop and estimation of the crop area and crop